Okay, we have just a little bit more to do in this chapter on carbon cycling, and then we'll finish that up, and then we'll start on the other nutrient cycles. And this is what we left the end of the last lecture on, is the diagram of the carbon cycle. And to remind you, the upper portion, the blue part, maybe you can think of that as water, is oxic, and the sediment, maybe you can think of this as anoxic. And then the inorganic forms are aligned here from the most oxidized to the most reduced, so the oxidation state here. And we see that in general, fluxes that are going from left to right in the oxic part are going with potential energy. And in general, fluxes that go from right to left in the anoxic part are going with potential energy. And this gets back to the whole redox thing, where a reduced compound in an oxidized environment has potential energy, but it doesn't have much potential energy in a reduced environment. In contrast, an oxidized compound in a reduced environment has potential energy, but does not have much potential energy in an oxic environment. And then the major fluxes we talked about, talk about, so respiration, combining oxygen and organic carbon, is that going with or against potential energy? With, good. And then how about photosynthesis or chemoautotrophy? Is that going over here? Is that going with or against potential energy? Against, good. Yeah, so it's taking oxidized carbon, and organic carbon is more reduced than oxidizing, so it's going against it. How about methanotrophy? Is that going with or against potential energy? With, good, Morgan, good, Sean. Yeah, and it's just really a specialized form of respiration, if you want to think about it. It's just that there's not that many organisms that can deal with methane directly. It's just a little bit more specialized, but it's still the same thing. They're oxidizing organic carbon and turning it into CO2. Methanogenesis goes with potential energy. You have to have really low redox, though, before the CO2 has enough potential energy. And so all the nitrate has to be gone, all the sulfate, about any of the other oxidized inorganic carbon, inorganic compounds in addition to oxygen. And then we are heterotrophs, right? So we reorganize and reuse. We like break down proteins into amino acids, take them in, and then build them back up into the proteins that we need. Same with lipids and all that. We respire away some of that organic carbon, but a lot of it we just sort of rearrange. And anoxic organisms can also rearrange organic carbon. They can create methane and fermentations. So these are anoxic respirations, and down here. There's one more thing that is on here that we haven't talked about, and that is anoxygenic photosynthesis. So historically, the times were when the Earth was anoxic, right? There still were photosynthetic organisms. They just weren't splitting water for photosynthesis. So they can use things like sulfide, and in this case, purple photosynthetic bacteria and other related organisms are able to generate organic carbon from CO2 in anoxic conditions using other electron donors in addition to water. So this is the carbon cycle. And as I said, if you really want to learn it, being able to sit down and draw it and get redraw it is probably the best way to do that, and in response to one of the questions that Emma had.